Hello, everyone. My name is Elham Khoda. I am an early career member at the University of Washington. I am presenting contribution number 25 on physics community needs, tools, and resources for machine learning. I'm presenting the poster in person. My email is elham.e.khoda@cern.ch, and my Slack ID is elham.e.khoda. In this short video, I'll try to give a summary of my poster. Machine learning is becoming an increasingly important component of the cutting-edge physics research, but it is computationally challenging to use machine learning. In the poster, I will discuss the machine learning needs of the physics community, particularly particle and astrophysics. In my poster, I will also discuss a few tools and resources that can satisfy these needs and their best utilization in the coming years. The machine learning needs are spread out across latency and throughput regimes. For the trigger application of the collider and neutrino and astrophysics experiments, the machine learning algorithm needs to be extremely fast. At the Large Hadron Collider experiment, there are about 40 million collision events per second. So we have very limited time to decide whether to store or discard a collision event. On the other hand, the offline algorithm should be throughput efficient, meaning we should try to process as much data as possible in a given amount of time. In coming years, we also expect to see an exponential growth in dataset in these experiments. To satisfy these needs, we have to use specialized hardware like GPU, field programmable gate arrays, or FPGA, intelligence processing unit, or IPU, etc. So far, CPUs were commonly used, but they are not efficient for machine learning inference. In the software side, there is an increasing trend of using open source industry tools. The community has also started to developing tools to satisfy specific needs. Apart from the tools, we also need to think about alternative computing models to address some of these future needs, like as a service paradigm where we use a client service computing model. In the future, machine learning will be applied in collecting data at a very high rate and processing them efficiently for all fields of physics. In particle physics experiments, we already use machine learning for several tasks. In the future, it is expected to see more and more machine learning-based algorithms across all steps of the particle physics data processing pipeline. For example, some initial study shows 17 times speed up in machine learning-based event reconstruction by using the client-server computing model in proto-Dune neutron experiment. Machine learning will help us overcome some of the challenges of physics research in coming decade. The computing challenges of using machine learning are expected to be addressed by specialized processors. Moving ahead, we need a coordinated effort between different science and engineering domains. Continued research, collaboration with industry, and high-performance computing centers will be critical in the future. To know more about physics needs, tools, and resources for machine learning, please come and visit contribution number 25. Thank you. My name is Elham Khoda.